Got a couple of mega batteries. Don't have to plug it in anymore, hopefully.
Oh, that's nice.
We'll see how they work. Okay, we got blue outline. We have the up here. Okay. Okay, time to get started, guys. No lab today, lab tomorrow, and Thursday, Wednesday and Thursday? Okay. Doing the unknown lab, okay? Everybody will get 2 unknowns. Any questions about lab?
Do you want us to turn the lab report in class or at lab?
Lab report turned in lab.
Okay.
When you come to lab. Okay, guys. As I said a little bit ago, we were rushing at the end. I don't think my intro explanation was as good as it could have been. Let's kind of go back and look at this. Okay, I've got a, this is going to be ethane. Okay, each carbon, these only enter actually H's coming off. Let's pretend they're H's, CH3, CH3. Okay, this thing, because it's a sigma bond, can rotate. And if it rotates, the groups on the end rotate relative to this. Okay, so we've got free rotation. Does it exist like this? Or does it exist like this? Basically, these are called different conformations, or sometimes called different rotamers. Now, the compound isn't just stuck here, because it can rotate. It's like, okay. Well, you can ask me, and when we say does it exist like this or this, we're looking at what's the best energy conformation. It's not going to just be stuck here, but it's all just sort of at equilibrium, which is favored type of thing. For example, when I'm at equilibrium, which is favored? This or this? Which is favored? This. My arm's down because that's lower in energy. So majority of the time you'll see me in this conformation. Okay? Walking around like this is just higher energy. My arms are going to get tired. Okay? That's the kind of thing. That doesn't mean I can't do this, but just this is the favored conformation. Okay, let's look at this. We looked at drawing these Newman projections, circle, circle, dot, dot. Okay? Hopefully we've covered this. We're looking down, this is the front carbon. And in the back we see the other carbon. This is sort of here, it's drawn on the board like this. Front, H straight up, boom, boom. Yeah? And then in the back, there's an H going straight up. Okay, you actually lose the 3D nature when you go to the Newman. Yes, these 3 on the front are actually coming a little bit forward. Okay? All 3 of these are coming a little bit forward. You'll lose that in this drawing. That's okay. We gain a lot of benefits. It makes it a lot easier to draw these. We need to know how to draw these. We need to know how to rotate, manipulate, and work with these structures. Here we go. Let's rotate. Okay? Now this is energy. It's relative. There's no absolute value here. This is higher energy than this. This is a rotation of, are they rotating, when we go here, did they rotate the front carbon or the back carbon? They actually rotated the back carbon. The front carbon is the same. When you do the Newman, you're really looking at 2 carbons, okay? You're looking at a carbon-carbon bond. They actually rotated the back. That's this. To get to here, we rotate the back there. Everybody agree that's that? The front is the same. The back, we now have H, boom, boom, and straight down. We no longer have a H straight up in the back. Now, that's a rotation of 60 degrees. Now, that's a different conformer, or a different rotamer that can be shown. Now, there's an infinitesimal number of rotations. For example, there's 1, there's 2. Okay, I could rotate a degree each time and call it a different conformation. Basically, though, you rotate like 60 degrees at a time. Okay. Now, why is this one higher energy than this one? Well, look, in terms of names, can you see, Fabian, the H, the CH bond in the back? Not supposed to be able to. Okay, if this one's right in front of that one, what do you call it when one's right in front of the other? Just like this, the moon is up in front of the sun. That's called an eclipse conformation. Now, if that H in the back was exactly behind the front H, you'd only see just one H. It would just look like that, right? You'd see, hey, the other one's right behind it. Well, we don't do that. We draw it a little bit to the side, a wee bit, because we want to draw it in. Otherwise, you'll say, hey, did they forget to draw the H? Is it back there? I don't know. But that's supposed to imply a total eclipse. But you're still going to see it when you draw it. But you want to know it's there. Okay, so we start with total eclipse. That's actually higher in energy. Now we go here. Is there a CH bond directly behind the front CH bond that's up? No, there's no longer anything back there. So it's no longer eclipsed. None of the bonds are eclipsed. Look at there. Is that one eclipsed with anything in front of it? No. None of the front bonds are eclipsed with back bonds now. Okay? So while that's all eclipsed, not only is that eclipsed, but look at there. That and that, or this is directly in front of that. Everything's eclipsed. By turning the back 60 degrees, now everything is what? Everything is staggered. So that's your terminology. Staggered is better, lower in energy. Why? Well, it may be hard to kind of rationalize it or kind of see here, but basically eclipse, the electrons are closer together. Okay? You turn them, and the electrons do move a little further away. There's just more space of the electrons when it is staggered. So staggered is better. Guess what, guys? Staggered is always better than eclipsed. Always. We're just turning the back. 60 degrees, what do we get to? This. Could you draw this and get that? What do you see? I see a carbon with an H straight up. And to the right, we'll do some more practice there. Let's go through this. We're rotating an entire 360 degrees around the back. Let's turn the back another 60 degrees. What do we get now? We actually get back to eclipse. And it's actually the same exact eclipse as over here, because all these are H's. There's no difference from that and that. There's no difference from that and that. So they have the same energy. We go back up. Now let's rotate again, another 60 degrees. We get back to staggered. But that stagger is no different than this one because they're all H's. Let's turn the back again, another 60 degrees. What do we get? Flips, another 60 degrees. Hold on, I turned it too far. Another 60 degrees. Staggered, another 60 degrees. Eclipse, another 60 degrees. Hold on, I think this eclipse is supposed to be the same as that one. If we had colored this one red, I think we'd be all the way around. We'd be all the way around, and that one on the end is actually the same as this one. Okay, so we started here and we did a 360 degree turn, 60 degrees at a time, and that should be 6 turns. 1, 2, 3, 4, 5, 6 turns takes you back to where you started. Okay, here's a question that could be asked you: how many different energy levels are there for rotation around the carbon-carbon bond at methane? How many different energy levels?
360.
Well, forget about we're 60 degrees. How many shown here?
2.
The answer is 2. Okay. You have this energy level, which could have some value if we put an absolute value on it, and we have that energy level. Boom or boom. Again, we're only considering eclipse or staggered conformations. We're only considering every 60. Not every 1 or 0.1 or 0.01. Okay. 2 energy levels. Because all eclipse are the same and all staggered are actually all the same. Let's move down below. And let's look at butane. Now butane, I'm going to actually take off 2 here. Now I'm going to say carbon, 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 4 carbons. But the two H's on this carbon, we're going to say the little nubs here. Small H's, small H's. There's 3 here, but let's not worry about it. We're just looking down the so-called 2-3 bond. If you name this, that'd be 1, 2, 3, 4. So that's the 2 carbon, that's the 3 carbon. Okay? So we're looking down the 2, 3. Now, conformations are shown below. Let's start with A. The methyls are meant to be what? They're actually meant to be eclipsed here. And that's how it is on the board. Front carbon, you got one straight up. Back carbon, you got one straight up. Front carbon, H here, H here. Okay? Now, is that staggered or eclipsed? Eclipsed. Okay? Dihedral angle. Remember we introduced that? Dihedral angle is the angle between the front bond and the back bond. For example, the back bond was right there. What's the dihedral angle, June?
90 degrees.
90 degrees. It's the front plane and the back. It's 2 planes. Dihedral. Okay? But what is it right there?
0.
A 0-degree dihedral angle. Okay? There is no angle there. Okay? If you turn it a little bit, now you got like a 2-degree or 3-degree angle, and 90, and what do you want to call that? 180 degree. That versus this. I think everybody sees that's 90, right? Well, then that should be 180. Okay? This is meant to be 0 dihedral angle. I think here they're turning which carbon? Front or back carbon?
Front one.
They're turning the front carbon here. Let's turn the front carbon to the right 60 degrees, and we get that. Okay? It's that. Back straight up. Front carbon, we have H straight down, H this way, and H that way. I mean a methyl that way. Is this eclipsed or staggered?
Staggered.
That's a type of one of these. First off, is it eclipsed or staggered? There's a bond straight up in the back. Is there a bond straight up in the front eclipsing the one in the back? No, it's staggered. Okay? Okay, let's go on before we hit what Gauss is. Let's rotate again, front carbon. We're going to rotate another 60. And we should have the third one. Now there's an H straight up. And there's a methyl straight up in the back. The H and the methyl that are both straight up are called what?
Eclipse.
They're eclipsing each other. This methyl and that H are eclipsing. This is all eclipsed. See, the methyl is eclipsing the H is eclipsing the H is eclipsing the methyl. Okay, but look, this one also eclipsed. But are these eclipsed the same? No, here the methyls are eclipsed. Here, H of the methyl is eclipsed. They're not the same. So if we plot this energy, A and C are not the same. Which is worse? Worse is going to be when your bigger groups are eclipsing. Okay, and methyl is bigger. Don't forget, this carbon has H's coming off. Okay, like H's coming off. And if these are eclipsing, they're like, that's going to be higher energy. If we can rotate, it's going to be better. Bigger groups eclipsing is going to be worse. That's why A is higher than C. Now, why is B better than A and C?
Staggered.
Because B is staggered, and we said staggered is always better than eclipsed. I think we said that 3 minutes ago. Okay? Let's go from C, which is that, to, we're rotating the front, to that. Okay, is that staggered or eclipsed?
Staggered.
You may not hardly be able to see the H's, but there's one here and one here. Is there one coming straight up? No. Look at the back. There's an H going that way. Is there an H here going that way? No. If you draw it, it's this. And none of them are eclipsed. That's staggered. But is this staggered the same as this staggered? They're not, because in this staggered, the methyls had a dihedral angle of 60 degrees. Here, the dihedral angle between the methyls is what?
180.
Kiara? 180, okay? You always want your biggest groups furthest apart. Which one of these has groups furthest apart? 60 degrees or 180? Here, biggest groups further apart. So while they're both staggered, this staggered is better. So that's why D is lower than B. Terminology. Yes, they're both staggered, but what can you call these? This one with the two methyls sort of very opposite to each other, 180 degree dihedral angle, is called anti. This one where the methyls are sort of to the side of each other. It's not eclipsed, but it's just a little to the side. It's called gouache, which I think that's French for to the side. I don't know. Anybody know French? Is that true? We'll go with that. It's called gouache, okay? Would you say the methyls are eclipsed? Would you say they're anti?
Yep.
What do you want to say they are?
Gouache.
It said they're gouged to each other. Okay? But gouache is not as good as anti, is it? Because anti, you got those big groups. They're a little bit like, okay, these electrons are repelling. Okay, now we're anti, and that's okay. I don't like that. I'm going to be more like this than gouache. Certainly not going to be eclipsed. Okay. Now I think if you keep going, we just get back, because at this point we're going past 180 and we're working our way back up to 0. The front is being rotated. It's now here. How do you want to describe E? First off, is it staggered or eclipsed?
Eclipse.
It's supposed to be eclipsed. You just have to kind of know it's either fully staggered. When it starts being like this is supposed to be eclipsed, but they're showing it just to the side so you can actually see what's being drawn. Okay? Then we get that. Methyls are back to gouache. And then we get back to there. Methyls are eclipsed. And that should be the same as this over here, right? Okay. Now if you go through this, B and F are actually the same. Because if you look at these so-called steric interactions, me saying the methyl likes to be away from each other, the clash of the electrons, or really the clash of the groups, is called sterics. And so eclipsed has a good amount of steric interactions, and sterics tends to be a bad term. When we go gouache, the sterics is less, steric interaction is less. Which conformation has the least sterics between the methyls? Anti, right? Okay, the least sterics. It's also the lowest in energy. So your anti is D. So your gouaches are F and B. They're low, but they're not as good as D. They're staggered, but they're not as staggered and as good as anti. And then your E and C are eclipsed, but I wouldn't call it like, what terminology do we want to, how can we tell between E and A? Because E and A are both eclipsed.
E is the local maximum.
We can call A something. A is when the groups are sort of not anti, but syn. That's why N, is that written anywhere here? Anti, I think you can sort of get. They're sort of opposite. It's anti. Here, this eclipse we could call like syn. S-Y-N. That's sort of analogous to kind of same. Or you could do this. You could say total eclipse. Okay? Where this is eclipse, but I wouldn't call it like the worst eclipse. What do you want to call this? Sometimes you hear partial eclipse. Well, you would say maybe the methyl and the H are syn here. That's not as bad as both methyls being syn. But usually when you just hear syn, it's like, okay, your bigger groups are what are being referred to, and your methyls are what are syn. That's what syn means. So how many total energy levels do we have? Or how many different energy levels do we have? You got your A level, that's 1. The CE level, that's 2. The BF level, that's 3. The D level, that's 4. So here we actually had 4 different energy levels, where with ethane we only had 2. Because here, not all the things are the same on these carbons. And so not all eclipse or eclipse are the same. You can have total eclipse or partial eclipse. So that's rotation, that's terminology. There's a little bit of view over here. These are your Newman projections. So that's this here. Eclipse, syn form. Methyls are totally, okay, eclipse. Now these are called space-filling models that are getting a little bit more close to reality to show the actual size of the atoms. This is just really just sort of miscellaneous information, but the anti is the best conformer. If you can kind of look at these and see the methyl groups, really how there's just more space through here. And when you get to the syn or the total eclipse, you can recognize what might be methyls, how they're just all jammed together. Really just a different view. Let's do some problems here. Okay, that was with like 2 groups, like 2 methyls. What about other groups? And what if we had more than 2 groups? What if we had 3 or 4 that we were having to deal with? Well, first off, here's the take home. You want your larger groups to be what?
Anti.
Anti. Okay? What's your larger groups? Anti. So if you got multiple groups, we're going to have to say which group is larger. Okay? Let's do some examples and see what questions come up. Each one maybe illustrates something different. Okay, draw the lowest energy conformation. Typically with alkanes, that means Newman conformation. Okay? For this first guy here with the chlorine and the chlorine, looking down the 1,2 bond, that comes from nomenclature. What's the 1 carbon? This one on the left.
Couple groups attached.
1, 2, 3, 4. Okay, you named it. That would be 1-chloro, 1-fluorobutane. Is that the name of the compound? Okay. 1,2 bond. We want to look down. The first number is going to be the first carbon we see, and so it's 1, 2. If we look this way, it'd be like 2, 1. So we want to stand over here. And so we'll look down through here. paint, I forgot how I drew my little man. Look through there. Okay, pretend I'm on the chair and I'm looking down there. What do I see? I see carbon 1 here. Carbon 2 is behind it, right? 1, 2. Carbon 1's in the front. Carbon 2 is behind over there. From my view. I'm going to draw what I see. Circle, circle, dot, dot. Here's the front carbon. What's on the front carbon coming straight down to my feet?
Fluorine.
Fluorine coming straight down. I'm drawing what I see. I see a fluorine coming straight down. Okay, on the front carbon. What's to my left? To my left is behind the board. And here's the board.
Chlorine.
What's going behind the board? Chlorine. Dashed means it's going back. And if it's going back, it's behind the board, right? If it's behind the board and I'm standing here, behind the board would be on which side? My right or left? My left. Because on the right is you guys. You guys are on this side of the board. Chlorine's on the left. If I'm looking down that bond, I see a chlorine to the left. I'm looking down the bond, the chlorine to the left, going back. What's coming forward on this carbon? H. So it's coming forward, okay? Here it is coming forward, right? I'm just going to move the board out some. Okay. Now pretend the board's here. It's still coming forward, right? There's that H. If I'm looking through here, is that H pointed out to my right or to my left? All right. What do I see? Draw what I see. It's right there. Okay? Now, carbon 2 is back there in the back. What's on carbon 2? What are the 3 things on carbon 2? There's carbons 3 and there's an ethyl on carbon 2. What else is on carbon 2? 2 hydrogens. Okay. On carbon 2, the bond to carbon 3, how is it projected? Is it projected towards you guys? Is it projected behind the board? Or is it projected sort of straight up the board?
Straight up.
Is it to my right? Is it to my left? Or is it straight up the board?
Straight up.
It's straight up the board. Straight up the board. That's 3 and that's 4. A dot is carbon 1. Where's carbon 2? It's behind carbon 1. And what's on carbon 2? Carbon 3 and carbon 4. We're not going to put this in any projection. That's just connected to carbon 2, which is in the back. Now, the rest is 2 H's. They have to be here and here. Because it's tetrahedral. If you want to draw them in, one is forward, and one is back. Here we go. Make sure you believe my view. Here I am looking down. And I see that carbon over there. Carbon 2. Here, let me do a model so I don't have so many fingers. Okay, forget about carbon 1. Carbon 1, there's H fluorine. Let's look back here. No, let's actually do this. Here are the 4 carbons. Boom, boom, boom. Boom, boom, boom. Okay. This is carbon 1. There's things there we've already drawn. Let's look back at carbon 2. What do I see? I see a bonded carbon going straight up. I see an H coming down and towards you guys. And I see an H going down and back. So I want to draw that. Draw a carbon straight up. Do I have a carbon straight up? Do I have an H coming down and towards you guys? Down and to the right? I'm drawing the same thing on the board. I'm just going to turn. This is the back carbon back here. Alpha straight up, that can rotate. You can draw that any way you want. Carbon straight up, H to the right, H to the left. Yes, these are going back a little bit. Okay, there you go. That's the original view. Is that the lowest energy conformation?
No.
That's the original. What's the largest group on the front carbon?
See
Which is larger, chlorine or fluorine? Chlorine is larger. Okay? With the halogens, we can just say the larger halogen is indeed the larger. Now, there are other things that go into that, and sometimes you're like, huh, why is bromine not considered as big as chlorine? You can actually look up tables, and they'll give you priorities for conformations. But for us, larger halogen, larger group, that's going to be the sort of priority group. Okay, back carbon. What's the biggest group on the back carbon? H, or ethyl? Ethyl. Okay? Right now, those two groups are what? What's the relationship right now? Right now, they're gauche. What's the preferred?
Anti.
Anti. Okay. Can you redraw this anti? Earlier we just rotated one carbon, right? Up the front, keep the back still. Why don't you keep the back still and just rotate the front? And when I say rotate it, just turn it like a dial. Okay? So draw the lowest energy conformation now. I'm going to rotate the front when I do it. Anybody have it yet? Anybody else? Brandon? You got it. You got it?
Yes, sir.
Let me ask you a question. You're looking at your lowest energy conformation? Okay. What's the dihedral angle between your fluorine and your ethyl? 60 degrees. Okay. I think that sounds pretty good. Let's see if we get it right here. Basically, where do you want the chlorine to be? Where it is, you want it to be over here. You do want it to be staggered, right? Check. Staggered, right? Okay, it can be staggered. It can be staggered between these two groups, between those two groups, or between these two groups. Where do you want it to be? I like to be anti to the other. So I'm going to rotate this bond this way. So move this down. So the chlorine will come down here. Okay. Where will the H go? I'm just rotating it. The H is going to swing over here. Chlorine moves down here what is it, 120 degrees? Yeah. The H swings 120 degrees here. The fluorine swings 120 degrees here. It's going to be dead right there. That's going to be the lowest energy conformation because your largest groups, which we identified, are anti. Very often what's wrong here, wrong answer, people would have fluorine here and H here. How did you get that wrong? That's because you got this wrong. That's because you put fluorine here and H here or something. You didn't draw the original right. First you have to draw the original right. If you get really good, you don't even have to draw the original. You could just put that up there. But I would recommend drawing this right because you do have some 3D view here. That chlorine is going back. We can also draw a compound with the chlorine coming forward. All right. There we go. Let's try these two. How about you guys on my right? Do the first one. You guys on the left side do the next one.
Are we doing the original or the most anti-configured?
So ultimately the question is draw it in the lowest energy conformation. Looking down the indicated bond.
Does it matter if we rotate the back one instead of the front? The back carbon instead of the front carbon?
No, you mean over here? I could have rotated the ethyl. If I rotated the ethyl, I would have wanted the ethyl to be here.
Okay.
But that would be the same thing as what we drew here. It would be just a different drawing. That's like me drawing a right hand on the board. I can draw a right hand on the board like that, or I can draw it like that. It's the same hand. On the 2, 3. That's going to be 2, 3. I'm looking down through there. Okay, I'm standing up here, I'm looking down. What's on carbon 2 in the plane that is going straight up or straight down? Methyl. Okay, that's a methyl on the end. I'll draw it into me if you want. Okay, coming straight down. Because that methyl is not going to my right or left. If it was going to my right, that means it's coming towards you guys, and it would need to be bolded. It's not bolded. It's not bolded or dashed. It's in the plane of the board. It's in the plane of. Here's the board right here. Okay, what's on carbon 2 coming towards you guys? Bromine. Okay? It's up there coming towards you. I'm looking at it from here. It's going towards you. That's on my right. I just want to draw what I see. I see bromine coming here. What's on carbon 2 going behind the board? An undrawn hydrogen, right? Tetrahedral. 2 in the plane, 1 forward. H must be back. So if it's behind the board, I'm looking here, behind the board is to my left. Hey, I see an H going to my left. There's an H going to my left. And I'm drawing what I see, H to the left. Really, here's the board. Okay? But I've just turned it. If I take this board here and turn it this way, the bromine's coming towards you guys. Okay? Okay, let's look at past carbon 2. Here's carbon 3 over here. What's on carbon 3 going straight up or straight down? Ethyl. Going straight down. Ooh, we already have something straight down. That ethyl is eclipsed with the methyl. What's on carbon 3? There's something on carbon 3 going behind the board that is back. What is that?
Methyl.
Methyl. So carbon 3 is going to, that's my left.
Yes.
It's eclipsed with the H. Now when you draw eclipse, you want to draw it a little bit to the side. I drew the back thing a little bit to the right.
Can I write ET instead of prime? Drawing that? Can I write ET like atom?
You could. I'm going to leave it like this, though. We have a methyl. I'm going to draw it actually below this H. Because it's to the low side of the H. The thing in the back is going to be, this one's going to be here. What's on carbon 3 to my right? It is back here, but it's coming out towards you guys. Yeah, there's an H there. The back carbon has an H coming to the right. Back carbon has an H coming to the right. That's actually drawn on the board in a eclipsed conformation. Okay? It's easier to tell in the Newman projection. That's clearly not the best. What would be the best? What's the biggest thing on the front carbon? H methyl or bromine? It'll be bromine.
Bigger than methyl?
Now, some of these, you might have, there are tables that will tell you their steric priority size. Okay. Here's what you guys need to know, and otherwise, I'll try to give you an example where it's clear. We know halogens. Chlorine's bigger than fluorine, bromine's bigger than chlorine, and iodine's bigger than bromine. As you go down, bigger. Alkyl groups. The bigger the alkyl group, the more, okay? For example, if you were comparing a methyl to an ethyl, which is bigger? Ethyl, okay? Which is bigger, butyl or ethyl? Butyl, okay? So halogens are easy, alkyls are easy. When you start comparing apples to oranges, it could get a little more difficult. For example, which is bigger, a chlorine or an ethyl? Okay? I would hopefully not give you one that requires you to do that. Okay, but I'm saying the bromine is bigger than the methyl. What's the biggest on the back carbon? Methyl, H, or ethyl? Ethyl. Okay, so then we can rotate it. I'm going to leave the front the same, so I can redraw it with an actual circle. And the front I'm going to leave the same. The back, I'm going to rotate. How much do I need to rotate the ethyl by?
60 degrees.
Yeah, the days are actually 60. I'll put the ethyl here. If the ethyl's there, where is the back H now? Back H should be there.
Back methyl straight up.
And where's the back methyl?
So you go.
There's actually a methyl on the front carbon and a methyl on the back carbon. Here's the methyl on the front carbon. There's the methyl on the back carbon. Here you go. You got your big groups anti. You might say, well, look, this and this are gauche. Well, you're welcome to put this methyl anti to the ethyl, but guess what? Then the bromine will be gauche to this. That's not going to be as good. You don't want your bigger group gauche. So yes, you just have to have this. We have our largest groups anti. Okay, looking down the 4-3 bond, what's the nomenclature here? That's got to be 1, 2, 3, 4, 5. That'll give us 2 substituents at the 2 position, where this way you only have 1 position at the 2 position. 4-3, 4-3. So we want to be looking down through here. I'm looking this way. On the front carbon. What? Well, if you look down the 3-4, you could still get the same answer. You'll just have carbon in the back versus my front. It won't be correct fully because you didn't draw it this way. Okay, what do we see on carbon, on the front carbon, carbon 4? I see something going straight up. What's going straight up? Methyl. What's coming towards you guys on carbon 4? Here's carbon 4, but there's something coming towards you guys. What is it?
Iodine.
Iodine. If it's coming towards you guys, that's my left. We might do a model at the end here. Okay. So that I see a carbon with an iodine to the left. Carbon with an iodine to the left. What's on carbon 4 going behind the board? Yeah. Since it's going behind the board and I'm looking this way, behind the board's on my right. Okay. Carbon 3 is over here. What's on carbon 3 in the plane? Is there something going straight up or straight down? There, I'm looking like this. Boom. What's going straight down?
Tert-butyl.
Tert-butyl. That's a tert-butyl going straight down. What's on carbon 3 going to my left? Brian? What's going to my left? Mackenzie? Yes. And what's on carbon 3 going to my right? As I'm saying here, my right, is that in front of the board or behind the board? I can't put my hand there, but it would be behind the board, right? What's going behind the board on carbon 3? An undrawn hydrogen, right? 2 in the plane, 1 forward, 1 back. The undrawn thing is going back. Going back is behind the board. If I'm standing this way, behind the board's on my right. I'm standing over here. Behind the board's to the right. It's also going sort of up. There we go. That's how it's drawn. Is that the lowest energy conformation? What's the biggest on the front carbon?
Iodine.
Actually, iodine. What's the biggest on the back? H-methyl or T-butyl? T-butyl. Okay. Now you can rotate either one. I'll rotate the front, I reckon. The back is going to have H, methyl, T-butyl. Iodine is going to want to move here, yeah, but it's on the front carbon, so it's there. Methyl moves here, H moves here. Your two largest groups are anti. Let me ask you something. If this H was a ethyl group instead, would you want to show a different conformation, or would it you just have ethyl group? Right. If this was ethyl, well, it would just be there. Because the T-butyl is still the bigger group. You wouldn't put the ethyl down here and put the T-butyl next to the iodine. So if this was ethyl, that would actually be your lowest energy conformation. Because your biggest groups are anti. But you could look at it and say, hey, look at all three of these groups. They're all gauge to each other. And while they're not eclipsed, Gauss is still close together, and you could actually somehow you could say, well, couldn't I have a situation where two groups are here and here? Possibly, but for us, what's the lowest energy conformation? The largest group's anti. Okay.
So in practice, probably the back group would be actually clockwise from what it is.
Actually, no, because anywhere you go here, you're going to have two groups gauge to the iodine. If I move this here, then I'd have the T-butyl and the methyl.
No. Not a full, like maybe 10 degrees or something. So the T-butyl is beside the hydrogen, the methyl's closer to the iodine, and or would it?
Oh, possible. But again, we're not considering 10 degrees. We're only considering 30-degree rotation. I'm sorry, 60-degree rotation. Yes. In real life, yeah, maybe it's not exact, like 109.5. Yeah, in real life, maybe it's 107. But we're just looking at completely eclipsed or completely staggered. Okay, questions about these?
So with the diametral angle between the methyl and the T-butyl groups, would that be 60? Or?
This here?
Mm-hmm.
Yeah, these are all 60. Because this to this is 180.
Mm-hmm.
And so it's 60, 60, 60. All the way around is 360. So you got 60, 60, 60, 60, 60, 60 for a total of 360.
So we won't do these with the carbons being gold on it.
The two carbons be double bonded?
Two face ones.
No, because then they would be trigonoplanar. For trigonoplanar, you really don't need to do this. You'd have two. You would only have two groups, but they would be planar, and actually the groups are always going to be eclipsed. If you look at a like an alkene, two groups coming off are always eclipsed. That can't be like that. Okay, question. Can a sin or Gauss conformation sometimes be preferred? We're saying anti is the best. But can another conformation be preferred?
Yes.
You have two large ones on both faces or something.
Well, this is ethylene glycol. Its preferred conformation is this. The two OHs are, they're not anti, are they? What are they? Yeah, that's known to be the preferred conformation. If you model this compound with very sophisticated mathematical modeling, it actually prefers Gauss. This is your lowest energy conformation. Why?
Hydrogen bonding.
If they're anti, they can't hydrogen bond. But they swing up, now they can start this magical hydrogen bonding interaction.
So that goes what we learned Friday in terms of the rotation of electron.
Does this make sense? You got two pieces of Velcro, sticking, holding them up there. Hydrogen bonding is a favorable interaction.
Would it be enough energy to pull them syn, or would they stay in the staggered?
I think probably staggered, because I think you can hydrogen bond like this. Yeah. Okay, while we're doing, so this is showing a hydrogen bond sort of from a Newman, right? We've done hydrogen bonding before in intermolecular. You know, I could just show, you know, a solvent, you know, like ethanol. Right, we showed like ethanol, hydrogen bonding to that. So that would be intermolecular. Two different molecules, like two different states, interstate, always two different states. But instead of inter, could you have an intramolecular hydrogen bond here?
Yes.
That's what this is. This is an intramolecular hydrogen bond. It's a hydrogen bond sort of internally. How could you show this without just going to a Newman projection?
Rotate the OH.
Well, you could just draw this. I mean, that's the same molecule, right? What have we done? Which bond have we kind of rotated? No, it's like we've rotated this carbon-carbon bond right here. Because if these groups are here, here are the two groups, the OH and the methyl. If I rotate this bond, okay, now the OH would be drawn up here. I'm rotating this bond. That puts it up here. Now we can have a nice hydrogen bond between the nitrogen. I drew that nitrogen kind of big, but okay. So really, I showed a different conformation, but I didn't have to show Newman. Okay. But we really rotated the bond. Now this guy is probably not going to, that H is probably not going to hydrogen bond to this nitrogen, it's just too far away. Here, what size ring did we make with our hydrogen bond? Now it's not a covalent bond, but what size ring is this? 1, 2, 3, 4, 5, 6. What size rings did we say are best?
6,
5 and 6. And so we can just nicely sort of hydrogen bond. Okay. Let's see if we can name one of these. Name this guy. Okay, here's the front carbon. Let me do this. There's the front carbon, there's the back carbon. What's on the front carbon?
Chlorine.
Chlorine.
I see a chlorine going straight up. Okay? I want to draw a chlorine going straight up. Okay, pretend like I'm over here. Here's the front carbon. The back carbon is away from you. What else is on the front carbon? There's something on the front carbon coming towards you guys. Or, I'm sorry, there's something on the front carbon going to the right. If it's on the right of this view, it's coming towards you guys. What is that? Ethyl. Coming towards you guys, though. I got an ethyl going to the left. For it to be going to the left on this carbon, it has to be going towards you guys or behind the wall? Has to be going behind the wall. Okay, look at the back carbon. Back carbon has 2 methyls and an H. If I want to draw this correctly, there's something going straight down on that back carbon. What's going straight down? Methyl. The H is going to the right. Going to the right, so the right would be what? Bolded, and going back would be a methyl. And there it is in a perspective drawing. We just went backwards. And so starting with that, going here, we started with here, and we got that. Any questions about that? Okay, at this point you could redraw it in even a cleaner line bond. We should be able to name it from here. Longest continuous chain. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I see 2 different 5s. Do you see anything longer than 5?
No.
So which we're going to go with if you got 2 5s?
The one on the right.
1, 2, 3, 4, 5. Anybody remember?
It should be
Starting from
One
right
with
to the
more
left.
branches.
Got 2 5s. Which one we want to go with?
The substitute on the lower number.
One with the most substituents, right? Which one has most substituents? Maybe going through here. Okay. And if that's, which is the 1 in? Doesn't matter which methyl you use, it's the same. If that's 1, 2, 3, 4, 5, is that going to be 1, 5, or is it going to be 1, 5?
Only one.
If this is 1, the first substituent is at the 3.
That's not gonna work.
If this is 1, the first substituent is at the 2. This is 1. 1, 2, 3, 4, 5 is pentane. What's on the pentane? At the 2, there's a methyl. At the 3, there's an ethyl and a chloro. Put those in alphabetical order: chloro, ethyl,
3 chloro.
3
3 chloro,
Four ethyl.
3 ethyl, 2 methyl, pentane. Okay, you can try that one on your own. Maybe look at it a little bit later. We need to now look at our last major topic for the test, and that is conformations of cyclohexanes. Very last page. Actually, there is no page. The blue. Yeah, the blue has a good bit. Okay, cyclohexanes. We introduced these before, and remember we showed the cis and trans?
Yes.
Cis and trans stereoisomers? Okay. We'll refer back to that once we get going here. So when we draw a cyclohexane on the board, we typically draw it like that. The problem is every one of these carbons is tetrahedral, and because of that, this ring is really not flat. Now if you draw a benzene ring on the board with the 3 pi bonds, that is actually flat. Cyclohexane exists in a non-planar conformation. For example, this. Benzene is planar. See how there's the plane? This guy, you see how it's not plane like that? Because of all the tetrahedral carbons. All right? So, what's the terminology here? How do you draw these on the board? Etc. Now look, if it was flat, I can make my model go flat. First off, it can't all be flat. You're going to have some H's coming to the side. But if we could just make all the carbons in a plane. Okay? Now there's just the carbon, the ring is in a plane. What do you see? What are the H's doing here? The H's are eclipsing. And those H's are eclipsing. If you look at them, all H's are eclipsing. See that, these two eclipsing? Okay? So, that's a driving force why the carbon is not all planar. Instead, what happens is, and you've got enough flexibility here, that one will sort of move up. Now the other one can move up too. And now the ring is no longer all 6 in the plane. You've got 2 sort of to the side, or 2 up. Okay? And you can set that here, and 4 of them, 4 bonds would hit the table and these would not. That's called a boat conformation. Sort of like an Italian gondola with the ends both sticking up. Okay? Well, the boat is not favored because these 2 H's are now coming close together. That's called flagpole interactions. That's not good. So that's boat. And I won't say anything about boat again, because boat is not as good as the next one. Instead, there's where it's flat, planar. Instead, one goes up, and the other, guess what? Goes down. And now if we look at the 4 in the plane, we can say, hey, 4 in the plane, but one is coming this way and the other is coming that way. And yes, what we have here is not a boat, but it's called a chair conformation. Why is it called chair? Because you can sort of sit here. This is coming up like the back of your chair. And as you sit here and you're back here, your feet can spill over and come down and rest on this down portion.
Because it's a lazy boy.
Lazy boy chair conformation. Okay. The chair is always favored because it doesn't have the flagpole interactions. Now, if we look at the H's here, remember before they were all eclipsed? Well, now let's look at down the bond. There's the front H. Is it eclipsed with the back H? You see that the H's are no longer eclipsed. See? The H's in the back are staggered compared to that one up. So by doing the boat or chair, actually this is the chair, the H's are no longer eclipsed. And that's a driving force for why you get the chair. And so there you go. It exists like that, and instead of like this, or this one being planar, all planar. So that's a limited view when we do this. How do we draw chair conformations on the board?
That's so much.
So draw that on the board. Here we go.
That's what I said.
Okay, draw two lines sort of like this.
Okay.
Parallel, slanted, and a little offset. And that's actually 4 carbons right there. We just need to hook these together with 1 carbon, hook these together with 1 carbon, we'll have 6 carbons on the board. This is going to get hooked together by doing a sort of a point like this. And this is going to get hooked together by doing a point like that. Now, of course, it's not going to look absolutely correct because that looks like it's a bigger opening and this is a little bit more narrow. That's because, well, I did it again, maybe it'd look a little bit better. That's essentially it. There's your 6, and there's the chair. You can sit here, here's the back, and your feet can spill over. Sometimes you'll see a drawing of a person sitting here, your feet spilling over. Okay? That's the carbon. Now drawing the H's though, because each carbon has 2 H's. Okay, here's terminology. Some of it may be my terminology. Some of the H's, let me set this thing on the table. Okay, here's the top. If I set this down, how many of the H's are hitting the table?
3.
Only 3. If I turn it over, how many are hitting the table? Only 3. There are 3 H's that are straight down, and there are 3 H's that are straight up. That's 6. The other 6 H's never hit the table. That's because they're sort of out to the side. They're equatorial. Okay? There's 3 H's straight up, 3 H's straight down. Or 3 bonds straight up, 3 bonds straight down. The straight up bonds are on the up carbons. This, and that are the up carbons. Sort of these 2 are up, and that's up. These get straight up bonds. And that's going to be like this. We're going to get a little 3D nature here. The other 3 carbons are down carbons. Does my up and down sort of make sense? Do you believe me? These 2 are down carbons. These get down bonds. And you sort of draw these like this. And there are your 6 H's that are straight up or straight down. We call those axial hydrogens. So C, understanding axial versus what's the other position? Equatorial or equatorial. 6 axial, 6 equatorial. Every carbon has an axial hydrogen. But importantly, it's either up or down. Every carbon also now has an equatorial bond. Here we go. These are a touch more difficult. This comes out, but how does it come? It comes out this way, to the side. Equatorial is going to be to the side. It's going to come out like this. How do I know where to draw that? That's because this bond is going to be parallel to not the carbon-carbon bond attached there, but this. This bond is parallel to these two. Is it? I mean, I draw that way? That is supposed to be parallel to these. Equatorial here is to the side. First off, you would never draw it this way. It's going to come here. But hell, is it parallel to this? No, it's parallel to this over here, the next bond. So draw that one in. Do you have this here with me? Draw that one in. It needs to be parallel to this. So that's going to be this parallel to these two. You want to go ahead and finish it up? Each one gets an equatorial that's parallel not to the connected carbon-carbon bond, but to the next one. Why don't you do this one over here on this tip? Draw that one in. Okay?
Yes.
That's parallel, not to the carbon-carbon, the first carbon-carbon bond, but the next one. See how that's parallel to that? This one, not parallel to the first one, but the next one, so it's parallel to that. And this guy, not parallel to that, but parallel to that one, so it's sort of, these are supposed to be parallel. Oh, we skipped this one. Not parallel to that, but to that. And see, these are almost parallel themselves, so it's never going to be perfect unless you draw it 5 or 6 times. But ultimately, look on that carbon. One H is axial, and the other H is called equatorial. This one would never hit the table. Okay? Like here. This here. That carbon is straight up, it's axial. This carbon is equatorial, right? I'll hold this carbon here. Is that a good share? Okay. There we go. This one's equatorial. If I flip it over, see that this one never hits the table. It's never straight up or straight down. There's 6 that never hit the table. There you go. There's a cyclohexane in what's called a chair conformation. Okay. Now, an important thing is identifying things as cis or trans. Look on the handout. Before we erase here, let's identify them here. Let me call this HA. Let me call this HB. And C and D. I'm just randomly picking. So let me ask you, is HA and B, are they cis or trans? Ah, before we said cis or trans, we did like this. Right? HA, HB, are those cis or trans? Trans, okay? Now, I don't have, this is not the same, because they're they're on adjacent carbons. Here they're not. Okay? But that's the same type of thing. We have a different view here. We need to be able to answer questions like sistertrans from this view. Now look at this. Let me see if this helps us along here. Okay? Now see, this is like the ring is flat. Okay? If we make this ring flat, not like a pancake, in this plane, are these two things cis or trans? Cis. They're both coming forward. Cis. Okay? Or flat like a pancake, they're both going up. And that would not be this, because this is where you would disconnect and put this one over here and make it trans. Okay? But what about a boat? First off, let's do this. Okay? They're trans. Green forward, red back. I agree they're trans. So let's make it a boat. What do we expect? First off, they're still trans because it's the same molecule. Can you tell they're trans? Well, this one's coming to the side. This one's. So how do you look at it? Is this equatorial or axial? Equatorial. What is this? Equatorial. Huh, they're both equatorial. Aren't they? So why are we calling them trans?
Opposite side of the...
That's because being both equatorial doesn't mean they're trans. Or doesn't mean they're cis either. Okay? We got to get to that. Let me show you how you get there. Okay. Here's how you get here. You're going to get the same answers if you did it this way, and I think you guys would call this the easy way. Here's what you need to look at. Is this H up or down compared to the other H's on that carbon?
Down.
It's down. That H is up. This H is down. Down H compared to that one. Everybody agree? It's lower on the board than that one is drawn on the board. Now, it has nothing to do with, now in terms of equatorial or axial, what is this?
Equatorial.
It's equatorial. It has nothing to do with this. And students all the time are want to say, well, they're both equatorial. I thought they were trans. I thought they were cis. I'm like, sorry, no. This is what, that's down compared to the H. How about this one? Is it up or down compared to the other H?
Down.
Okay? It's down compared to the other H. They're both down compared to the H's. They're cis. And if you drew this, if you put together this molecule and made it flat and then turned it, you would find that they're both pointing to the same side. I'd have to take time to do the model, but hopefully you believe. Here's how you do it. Okay? So H, A, and B are what? Cis. Okay? What about B and C? What are B and C? Well, B is down compared to the H, the other H that's there. C is up compared to the H that's there. So B and C are trans. Now, in terms of axial or equatorial, C and B are both what?
Axial.
C and B are both axial. But that don't make them cis. They're actually trans to each other. And if you drew this molecule flat, you would see them both pointing to the same side. Okay, what next do you want to do?
HCHD.
Which one?
HCHD.
C and D?
C and D.
C and D are what?
Cis.
That's up compared to the H. That's up compared to the H. C and D are cis. Now actually, if you look at both of the cis's, one is axial, one's equatorial. One is axial, one's equatorial. Maybe C, D. How about E? C and E are,
Cis.
what are C and E?
Cis.
Cis. They're both axial, they're cis. Yeah. But these are both axial and they're trans. So you can't mix the two. It's either up, down. Okay. There we go. Now, let's look another way. Identify H as cis or trans. The first molecule.
Trans.
Chlorine and the bromine. Now, whenever we draw these, you may not see all the H's drawn in. But you need to know how to do it because likely on the test it's going to ask you to draw in all H's or to draw in certain H's. For example, if you drew the H here, how would it be oriented? Be straight up. And if you drew the H here, how would it be oriented? Straight down. That's an up carbon. Where's the other up carbon?
In the middle.
There's this one here. Okay. So that's H. Chlorine and bromine. Are they cis or trans? Trans. Well, it's down compared to the H. The bromine is up compared to the H. They're trans. Do the other three. You guys on the right do the second one. You guys on the left do the third one. You guys got it? Veronica? Cis. Up compared to the H, up compared to the H, cis. Over here.
Trans.
Riley? Trans. Up compared to the H, down compared to the H. Trans. Okay, let's do this guy. Whoa. Shows a perspective drawing. Okay. Perspective is where we sort of draw the ring flat and do the dash to bold. Like we were introduced to a day or two ago. Okay. That is a cyclohexane, right? It is very common to just draw it flat on the board. All right. Although we already know that that's not a true representation of, all those carbons are not in the same plane. But it's common. Okay? So show it with the, if two things have a bolded bond, we call them cis. They're both coming forward. First need to start with, what's the relationship between, what do you want to call this group? No, common name, isopropyl. Common name, isopropyl. Between the isopropyl and the F, what's their relationship? Cis or trans? Okay. These are cis. What's the relationship between the F and the bromine?
Trans.
Trans. And that would probably, if we got this right, everything would be right, because if these are right, then this has to be right. And these are what?
Trans.
Yeah.
Yeah.
Okay, we want to make sure all that is. Now, I just cannot draw these. There we go. Okay, you can begin a variety of ways here, as long as you end up with the right answer. I'm going to put okay. I'm going to put bromine. Somebody got it? I want to look at somebody's. Okay. We do have to look out for what's called the mirror image. I would let you probably slide on that here because that's test tube material. But when you get through the course and you look back, if we had the wrong answer, it's because I let it slide. We're just looking at where are we at? Which one? No, you got a big problem there. And that's the problem I was looking for. Okay. I'm going to put one up there. I could have put the bromine anywhere. I could have put it dashed or bold. And actually, that's where you could have got the mirror image. There. From there, though, I have to be careful because is the fluorine here?
No.
No. The fluorine is two-away. I'm actually going to try to get the right mirror image. So I'm going to go this way. We'll put the fluorine here. Here we go. This is the important stuff. At this point, we got to do something specific. We're going to draw it here, dashed or bold.
Dash.
Well, they're trans, so we want to draw a trans. Okay? Now, the isopropyl is on the next carbon. And it's cis to the fluorine, so we want to draw this also dashed. And by default, lo and behold, the isopropyl and the bromine are trans, like they're supposed to be. There you go. So now those have the same relationship as we saw here. Indeed, this is the same compound. This is more in the view of, okay, here's a chair, and the groups have coming off here. But if we drew it on the board in a classical just board representation, then they would have certain forward or back. Okay, I don't have the exact model.
If you flipped all those, it would still be correct.
Do it.
If you said the bromine was dashed and everything else was bold.
If that was dashed and bold and bold, I would let you slide, but you would actually have the mirror image. You'd be okay for now.
Okay.
You'd be okay for now. When we get to test 2, you wouldn't be okay.
So how would you name that thing?
How would you name this thing? We don't have stereochemical in our naming. You would name this. What's the one position here?
Isopropyl.
1, 2, 3.
4.
It's a cyclohexane with a 1. If you did IUPAC, it would be 1 methyl ethyl. That's a 1 methyl ethyl. The 3 bromo. No. Alphabetical. It'd be 3 bromo. 4 bromo. Sorry. 4 bromo.
Two fluoro.
One
two fluoro, one. At the one we have a 1-methyl cyclohexane. That's all one word. This is IPAC. If you want to call that an isopropyl, the I would take precedence and it'd still be in the same place, one isopropyl.
So we're not going to call them cis or trans or anything like that yet?
That's actually difficult because once you get more than two, if there's only two, you could call that cis. Once there's three, you're like, what does cis refer to? Because those are cis, but these are trans. It gets more complicated. Once we get into test 2 chemistry nomenclature, we might do a little bit better. We'll still never really able to do completely.
So for now, that's acceptable?
Yes, for this now, that's acceptable. Okay, we didn't look at, a lot of times you might see this discussed first. Which is the favorite position, axial or equatorial? The favorite position is actually equatorial. Say I have some big old group, okay, like a, what's that, a isobutyl? Okay, big old group coming off my cyclohexane. Well, look at this. Does everybody see the cyclohexane here is in what type of conformation? Chair. You see the chair? In this here, the isobutyl is what position? Equatorial. You see that down H here? It's equatorial. And what can happen here is you can do ring flips. Okay? Here we were doing rotations. This can't rotate because it's in this ring. What it can do though is this can come up and this can come down. And that's sort of that's called a ring flip. Now when I know the ring flip, I'm to another chair, but this chair is different because now the big old isobutyl group is what?
Axial.
It's now axial. Okay? And the H is equatorial. Now which is better? Well, I already said. It's better for that to be equatorial. Why? Because if we do axial, the reason it's said to be is because this group clashes with the other two axial groups. Now they're H's, but see how it can swing around and clash with them? That's called, if this is 1, 2, that's 3. 1, 3 diaxial interactions. And if that's 1, this is 3. This interacts here, causing this to prefer to move away, this to come up, and you actually get the chair where the other chair. And if you look at this, it has more room. It doesn't have those interactions as bad because it's not coming straight down, it's coming to the side. In the end, to the side gives you more room. That's easy to know, right? The reason is because axial, you have the so-called 1-3 diaxial interactions. And any textbook in organic chemistry is going to make note of that. So, just like this, which is favored? It's going to be favored to be equatorial. Now, what about, Martin?
What if the equatorial, what if the axial position create a hydrogen bond for that interaction?
Then there may be something that makes something favored. Yeah. Hydrogen bonding can always, you know, mess with things. You'll see a lot of times with equilibrium. Now, one thing we need to do is we need to draw both conformations. We'll do that. First off, some equilibrium. If you got a methyl on your ring, first off, that's going to be favored, right? Equatorial? How much more favored than this? It's 18 times more favored. Okay. Sort of like at equilibrium, sort of 1 to 18 ratio. Now, if you make this a T-butyl group, it's 4,800 times favored. Because the bigger group is going to say, hey, I demand more room, and I'm not going to the axial position. You're only going to find me in the axial position 1 out of every 4,800 molecules. Okay? So that's typical what you might see. What if you have 2 groups? Which one's going to prefer to be equatorial? The larger group. So which one is favored? They're both chair conformations. This is favored chair conformation with the T-butyl group being equatorial. Now, one thing I didn't do, and I should do this, is doing a ring flip on the board. Let's redraw a cyclo. Actually, you can practice redrawing it, or you can look back at what you drew on your page earlier. I'm going to redraw the whole thing in here. Okay, this is supposed to be it on the board. These bonds are not as long. If this was long, we could see the back of the chair come up more. Up H, up H, up H. Okay, these models are just quite big enough for you guys to probably see it there. Okay, let's do a ring flip. When you do a ring flip, one end comes up. Now that's a boat, right? And the other comes down. And now we have, again, a chair, but now this side is up and this side's down. Now your book may talk about how when it goes from one to another, it might talk about something like a twist boat or a twist chair. That's just as you go in between. We're just talking about the 2 extremes. Chair, though. How do you draw the other chair on the board? Really, this comes down, right? We pull this down, and we pull this end up. Now, to get that one, we drew 2 lines like this. To draw the other, we're going to draw 2 lines the other way, like this. And now we hook these together like this, and these together like that. And so that's where this end has been pulled down, and this end has been pulled up. Drawing the H's, that's an up carbon, that's an up carbon, that's an up carbon. We get up bonds, down carbons get down bonds. And equatorial would be like this, this, already parallel. Not that one, but one away. This is actually supposed to be parallel to that.
So the HA, the first one, that was axial, is now equatorial.
We're going to find it over there. Yeah. If we start here, the HA is straight up. I'm going to make it that HA green. It's supposed to be sort of like that. There's supposed to be the back. Here's the footstool coming over here. When we do the ring flip, this comes down, this comes up. Now here's the back and there's the footstool. Yes, importantly, here the A is axial, but how is it now? It's equatorial now. And where's the A over here?
Far right.
Here's a simple take-home, guys. Whenever you do a ring flip, all of your axials go equatorial, all of your equatorials go axial. If you look at these, all 6 of these axials are now equatorial over there if you go through time to see them on there. Okay? Now this is drawing for the ring flip. There's another way to draw ring flips. That is, if I drew a ring flip to this, I would redraw it just like this, but I would just change everything from axial to equatorial. We may see that later on. So I'm never going to again draw something, pull it down and pull it up and redraw it. I'll just sort of, I'll just switch groups. Because I know if I did that, groups would get switched, so I'll just switch the groups. That's the way I'll do it later on. Okay, let's finish up here, guys. Show the following lowest energy conformation. And this is where we could see this. How many groups are equatorial in the best conformation? Let's do the first one. Show the first one in the lowest energy conformation. First off, it's going to be a chair. Next, it's going to have the largest groups equatorial. What's the larger group, bromine or fluorine?
Bromine.
Bromine. Ah, but you got 2. Are they both going to be equatorial?
Yes.
No. Not necessarily. They both have to be cis. They're cis to each other. Can they both be equatorial, be cis? I'm not sure. I didn't memorize that, but when I start going, I'm going to make sure that the bromines are cis. Because they're cis, right? The bromines are cis. Okay, here's how I would do it. Well, I know I can get one bromine equatorial. What I don't know is can I get both? I'm going to draw this. Now, I'm also not going to worry about that mirror image thing. I'm going to put one bromine equatorial. Since I did that, and I put it there, where does the next bromine go? Well, it's on the adjacent carbon. It's either there or there. For us, either would work.
What have we done?
I'm trying to figure out the mirror image, waste time on that. Let's put it here. Is it going to be equatorial or axial?
Axial.
Why axial?
Down carbons down.
Why does it have to be axial? Douglas, why does it have to be axial?
Cis. It's cis.
Because it's cis. The only way to be cis to that is to be axial. But hold on. I thought equatorial was the preferred group for bromine. Preferred place. You see, you can't have them both in this example. Maybe in another example you could. You can't have them both. Now, now where does the fluorine go? Okay. I'm actually going to put the fluorine here because I think it's going to get the right amount. You can put it here and you'll be fine. I'm going to put it here though. Okay? That means we're going to have bromine, bromine, fluorine. So this is actually the bromine that's in between the two groups. Does the fluorine go axial or equatorial?
Equatorial.
Yep.
Well, it's going to be trans to this one. Trans would be cis.
Mhm.
There we go. And we're out of time, guys. Okay. Please do the next one for tomorrow. I'm thinking we should delay the test today. Anybody have any objections?
Delay it one.
Test is scheduled for tomorrow?
Yes.
Yeah. Any objections to delaying it? Okay. I would have liked to finish up a little bit earlier. Okay. I don't like to rush too much at the end. Not a lot of chance to ask questions. Okay. Tomorrow we'll see what last questions are here. I think it's best to have test on Thursday. Yeah. So tomorrow we will start test tube material after about 10 minutes of questions. Okay? Everybody good?
How long is this? How long is this?
Test will be